Okay, morning for everyone. It is a great pleasure to introduce Professor Amie Wilkinson. She is from University of Chicago. Amie received the Bachelor of Arts degree in mathematics from Harvard University and the PhD in mathematics from University of California. She was the recipient of the 2011 Sutter Prize in Mathematics and gave an invited talk in the International Congress of Mathematicians in 2010. In 2013, she became a fellow on the American Mathematical Society for contributions to dynamical systems. In 2019, she was elected to Academia Europe. In 2020, she received the Levi L. Conan Prize of the AMS. She was elected to American Academy of Arts and Science in 2021. In recent work with Arthur Ávila and Sylvain Corvisier, she proved the formulation of the ergodic hypothesis for systems with positive entropy. In the C1 topology, ergodicity is generic. Besides this, Amie is a great researcher and a great speaker. It's an honor to have you here, Amie. It's your time.
Okay, great. Thank you. So thank you very much for this invitation. And it's a real pleasure to speak, to honor and celebrate women in mathematics, which I hope to do in this short talk. So the theme of this talk is dynamical symmetry, which has been a topic that has interested me, been interesting me for a while now, in fact. And I'll say something about some work of other people, notably women, in this topic, and also some work of myself and collaborators. So what is, first of all, what is symmetry? Many people from the waiting room, I hope that's okay. So what is symmetry? Well, we usually talk, when we think about symmetry, we think of it as a property of an object. An object is symmetrical if what? If it's very balanced, if it's kind of beautiful, it's well proportioned. Well, let's try to be a little bit more mathematical about it. So instead of talking about symmetry as a property, let's talk about symmetry as itself a noun. So what is symmetry a noun? A symmetry of an object is a motion that leaves the object unchanged. So let's pick my favorite symmetric object. I live up in Chicago where we see a reasonable amount of this, but this might be a little less familiar for those of you in Brazil. So a symmetry, what's a symmetry of this object? Well, what is this object? A snowflake. And we say that something is a symmetry, it's a motion that leaves that shape unchanged after it being performed. And so, for example, if I rotate a snowflake through a 60-degree angle, I get the snowflake back again, or something pretty close, right? But an idealized snowflake, you get the same snowflake back again. And similarly, you can rotate 2 or 3 times. You could rotate all the way around and come back to the original snowflake. But there's another symmetry in this snowflake, and that's where you can pick it up and you can rotate it and put it back in the plane. So I just did that, performed that twice. Whoops, I just performed that twice. But the flip is also a symmetry. So the symmetries, the notion of a group actually really comes from the idea of symmetry. And so it shouldn't be surprising that the collection of symmetries of an object form a group. So in this case, it's the dihedral group. You have 2 generators, A and B, A being the rotation by 60 degrees, and B being this, say this one of these flips around the axis, any axis but a flip. A has order 6, B has order 2, and they satisfy this relation. So there's an example. Okay, so now what do we mean by a dynamical symmetry? So a dynamical symmetry should be a motion of a dynamical system that keeps the dynamics unchanged. So let me talk about the context that I study, and that's smooth dynamics. So a smooth dynamical system is just an R times continuously differential map, F from a manifold to itself, usually a compact manifold, for some, where R is some integer at least 1. Okay, so that's what a smooth dynamical system is. What should be a symmetry? Well, it should be something I can reverse. So a symmetry should be a diffeomorphism, not just a smooth map, because, well, for the reasons I just said. So we say that a diffeomorphism H is a symmetry of F if it commutes with F. Or another way of writing it, since H is a diffeomorphism, is that H composed with F composed with H inverse equals F. And when you write it this way, you see that symmetries preserve any sort of dynamical feature of F, even features that involve the derivatives of F itself, should be kind of preserved by a symmetry. So for example, the simplest is orbits of F. Okay, so I'll say that in one more slide. Before I say that, I just want to note that because I choose my symmetries to be diffeomorphisms, they form a group under composition. So they're a subgroup of the group of diffeomorphisms. So the identity is a symmetry. I can always reverse a symmetry. There's always an inverse. If H is a symmetry, its inverse will also commute with F. And the composition of two symmetries is a symmetry. Okay, so we define S of F to be the group of symmetries of the dynamical system. Okay. So now, if my dynamical system is also a diffeomorphism, meaning that it has a smooth inverse. So in particular, it's a homeomorphism. So if F is itself a diffeomorphism, then all the iterates of F, so F composed with F, which we denote by F squared, F inverse of F is also a symmetry of F, because if we use this notation to denote F composed with itself n times, if n is greater than or equal to 0 or greater than 0, identity if n equals 0, and F inverse composed with itself, absolute value of n times for n less than 0. So this is standard dynamics notation. So if we denote F by this, then we have that F to the n plus m composed is equal to F to the n composed with F to the m, but that also equals F to the m composed with F to the n. So all the powers of F, including the identity and the inverse, are also symmetries of F. And so this is kind of a trivial, these are like what you would call trivial symmetries. By the way, what this means is that, because I didn't really say too much about dynamics, but F to the n, F should be thought of a way of passing time in your dynamical system. So if I have a point X and I apply F to it, I get F of X, and that's supposed to indicate where X is 1 unit of time later. And so this is saying that if I put an X here, this says that where X is in N plus M units of time is the same as where it is, looking first where it is in M units of time and then N more units of time, and that those should be the same. Okay. So we have this relation that the iterates of F, or the group generated by F, or the subgroup, is always a subgroup of the group of symmetries. And in fact, you can check it has to be a normal subgroup. Okay. So any questions? Okay. So now, this is a slide that should have gone earlier. Symmetries map orbits of points to orbits of points, but maybe this is a good place to put it. So here's a point X in M. There's F of X, F squared of X, just keeping the notation I did on the previous slide. There's F in 3 days, F in 4 days, and so on. That's called the orbit, or in this case, the forward orbit of X. And that's a fundamental object of study. And if I have a symmetry, H, then I can look at the orbit of H of X under F. Right, there we go. And the fact that F composed with H is H composed with F tells us that this is a little commutative diagram I just drew. But then you can move this little commutative diagram down the orbit, and we get that H sort of takes the whole orbit to the whole orbit. So that's one reason why it's good to think of a dynamical, of defining dynamical symmetries in this way. Okay. Now you can start looking at other invariants in dynamics. I want to focus on a special class of orbits. So what's the first simplest special class of orbits? Well, these are just periodic orbits. So you say that X is periodic. Oops. Yeah, I thought this might happen. Yeah, I don't remember how to go backwards. So we say that X is periodic if f to the k of X is equal to X for some k. And you could pick k greater than 0. And you can pick k to be the first positive integer such that this holds. And then that's called the period. Well, if f to the k of X is equal to X, then f to the k, let's consider h of X. Well, f to the k of h of X equals h composed with f to the k, because h commutes with f. It also commutes with the powers of f. And that's h of X. So we've shown that h of X is also a periodic point. And it has, you can also see that if this was a not equals, then you get a similar argument. And so what this shows that if I look at the periodic points, maybe I'll write it this way. I take the fixed point set of f to the k. This is equal to the fixed point set of f to the k. And H is a diffeomorphism. Oops, little f to the k. H is a diffeomorphism. So, if an orbit has f to the k of X, if it has k points, then H of it will also have like k points. Okay. And periodic orbits are very special. In some dynamical systems that are classically studied, you have a lot of periodic orbits. You have a dense set of periodic orbits. And so if you want to study the symmetries of a system that has a lot of periodic orbits, you've got a lot of information because you know that the symmetries preserve the periodic orbits. Okay. And then also wandering and non-wandering orbits. So, so in the case where M is compact, one can associate to M, a subset of M called the non-wandering set of F. It's a compact subset of the manifold. And this is the set of all points in M such that there exists, such that for every neighborhood U, open set U containing X, there exists an N greater than 0 such that F to the N of U intersect U is not empty. That's the so-called non-wandering set. I like to think of it in many ways, it's the set of points where the interesting dynamics take place. And so the claim is that if H is a symmetry of F, then H of the non-wandering set of F is equal to the non-wandering set of F. And let's see why that's true. So if I have a point that's not in the wandering set, so X is not in the wandering set, that means there's some neighborhood of X that never returns. That's a neighborhood, a wandering neighborhood of that point. And I want to show that it's enough to show that H commuting with F takes points that are wandering to wandering points. Okay. Well, H takes orbits to orbits, and it's a diffeomorphism. So, here's H of X. There's this open set. It's a diffeo, so it can't. So if this is a neighborhood U, here's H of U. From the picture I drew before, you see a very similar picture, right? Instead of having the neighborhood U, I have the neighborhood H of U over here. But these guys have to be disjoint. This has to be disjoint from itself as well. And if I take a smaller, any neighborhood here, and I take its pre-image, because H is a diffeo, it's a neighborhood here. Oh, I just need a wandering, sorry. I should say what it's not for every. So X is wandering. So X is in the, I didn't really say this. This is all I need. Implies that there exists a neighborhood U of X such that F to the U, F to the K of U intersect U is empty for all K. Okay, so if this forward orbit is empty, then if I take H of U, I get a wandering. Okay, so H preserves wandering points, and so it preserves non-wandering points. All right. And there's a very closely related, there's a very closely related notion to the non-wandering set in complex dynamics. The definition is slightly different. It's so closely related, though, I don't want to define it. So if I have a polynomial P from the complex plane to itself, so first of all, that's not compact. But you can define, you can associate to that polynomial a set called the Julia set. And it's like up to like some points. It's basically the non-wandering set in this particular case. And if H is a symmetry of the polynomial, then you can easily see that H preserves the Julia set of P. Okay. All right. So that's good. I just erased, I just wrote over. Okay, but this is true for the non-wandering set, but it's also true for Julia sets. Okay, and so I have some pretty pictures to illustrate this, but I should have put a picture of Laura DeMarco because she's a woman in math that Laura DeMarco made for me. So it's not hard to cook up a polynomial that has symmetries. So here's an example, but it's sort of not as easy to get one where you have a pretty picture. So here's a polynomial and here's a symmetry. So if I take a complex number that's an eighth root of 1, you'll notice that if I take and I multiply, so this is a rotation by 2 pi over 8, and I plug in h of z into f, a little calculation using the fact that this zeta to the 9th equals zeta gives you that we have this symmetry. And here's the actual Julia set associated to this polynomial. And we know that the symmetries of this Julia set actually has to contain this subgroup generated by H. And you can see that, in fact, there is this rotational pi over 8 symmetry. And so here we go from a symmetry of a dynamical system back to a symmetry of an object that's canonically identified with that dynamical system. And here's another one, just hearkening back to the snowflake. This has 2 symmetries, and in fact, no more. The 2 symmetries that it has are, well, this is multiplication or rotation by pi over 6, or 2 pi over 6, 60 degrees. And then there's this extra symmetry, g of z equals z bar. And complex conjugation is the symmetry of this set, of this dynamical system. The reason is because the coefficients of f are real. So if I plug in z bar, it's the same as taking the bar of h. Okay, and so the symmetry group contains the dihedral group. In fact, it equals the dihedral group, and you get a Julia snowflake. Okay, so I want to say a few things about flows. So flows are dynamical systems that are generated by vector fields. A flow on a manifold is a map now from M cross R into M. And it has the property that if I take, so I write phi TP for the image of P comma T under this flow. And it has the property, so you want to think of phi T of P as saying where P is in T units of time, just like F to the N of P was where P is in N units of time. And you want the flow to have the same property as iterates. And so you want phi T of, that if I take, if I go forward in T plus S iterates, this should be the same units of time. This should be the same as going forward in S units of time, followed by going forward in T units of time. Okay, that's to make it like a dynamical system. Okay. And now given a flow, oh, and I want it to be smooth, okay, just like my discrete time dynamical systems. And now we can consider symmetries of flows, both as, we can think of them both as, we could think of diffeos commuting with flows, and we can also think of flows that commute with flows. So let's talk about flows that commute with flows. And so we say that a flow is a symmetry of another flow. Well, we want these two things to commute for all S and T. So it's a kind of a stronger property than a diffeomorphism commuting with a flow. But it's very similar to saying, you know, if I know that FH equals HF, then that tells me that F to the M, H to the N equals H to the N, F to the M. And so this is the analog, because that wouldn't sort of follow automatically from just taking elements of the flow. Okay. And so if I have a flow, and now I look at the diffeomorphisms that commute with the flow. So I look at, I take an element of the flow. So let's consider F to just be what's called the time one map of the flow. So that's a diffeomorphism that just pushes you forward one iterative time. And if I take that to be my F, and now I look at the set of I take the symmetry groups of F, then the set of diffeomorphisms that commute with the time one map has to contain, it has to contain anything that commutes with the flow. And in particular, the symmetry group of F has to contain the flow itself. Okay, so this contains, in fact, as a normal subgroup, something that's either the real numbers or the circle, but anyway, the flow itself. Okay, so that's what I wrote here. Okay, so let's turn it on its head. If we know that F is the time one map of the flow, then it has to have the real numbers as its group contained in its group of symmetries. That means it's got a lot of symmetry, right? It's got a lot more symmetry than these snowflakes, right? It's got like a Lie group worth of symmetries. So this is, if you like, it's a Lie group. It's uncountable. It's big. Okay, so the time one map of a flow has a lot of symmetry. And if I had a diffeomorphism that didn't have that much symmetry, then it can't be the time one map of the flow. I'll come back to this. So the theme of this talk is that symmetries are special, which I hope, I don't know, should almost be obvious, because it's certainly objects that are symmetric we think of as being special. So they're also special in dynamics. So I want to illustrate this. First, just telling you a little bit about Noether's theorem. So symmetries in physics, in the right context, correspond to conserved quantities. And this is Noether's theorem. And there's, I shouldn't say conjecture, but there's a question of Smale that asks whether the typical dynamical system should have the least possible, the minimum possible symmetry. So a diffeomorphism, the only symmetries should be its iterates, typically. Given a flow, the only symmetry within the group of, the flows commuting with it should be the flow itself, and so on. And the third is a topic of my current research. I won't say very much about it, but it's this notion of symmetry rigidity, which says that at least in the right, somewhat tightly controlled situations, if you have more symmetry than expected, then it gives you a lot of information about the dynamical system. Okay. So first, Noether's theorem. So in words, Noether's theorem says that if we have this closed physical system, one that obeys the principle of least action, if you know what that is, then whenever you have a symmetry of the dynamical system, that should correspond to some quantity that is preserved. So in this particular case, you have a top, and you will agree, if you think of kind of, there's some big dynamical system that I won't describe for this. So it lives in a bunch of dimensions, not that many dimensions, but a point in this dynamical system, a quote unquote point, should be a top, a position of the top, and some kind of momentum, maybe, of the top. So it's like, how fast is it spinning, and what axis is it spinning? Okay, so I hope it makes sense that if I put my top in a position like this and I start it spinning at some rate, and I watch how it goes over time, and now I take that whole picture and I rotate that rotating the top around this axis by some angle. And instead, I start here with the same speed or whatever, and the same angle, that the motion here and the motion here are the same. Okay. So that says, you can move your frame of reference and you see the same thing. But that's the same as saying that the trajectory, the dynamics of this top commutes with this rotation around this axis. So there's the dynamical system here that's kind of hidden, which is a rotation around this axis. That's a symmetry of the dynamics. And what Noether's theorem says is if you have a symmetry like that, there's actually a quantity, there's a number that you can associate to any configuration of the system. And that number stays the same whenever I just look at an orbit of the system. And in this case, the number is something called angular momentum. And that's preserved by this top. Okay. And so more formally, I'll just say a few words. In the context of Hamiltonian dynamics, this is where you can state Noether's theorem. So formally what goes on is we have something called a Hamiltonian. So we think of ourselves as living in R2n. We have coordinates on R2n. There's Q1 through Qn, and there's P1 through Pn. We can think of Q as being position coordinates and the P's as being momentum or velocity coordinates. Okay. And a Hamiltonian is a way to associate to any position and momentum in this huge dimensional space a kind of an energy. So it's just a smooth function defined on this space. And we call it a Hamiltonian, and it represents the total energy of the specific configuration. So it's a specific configuration inside of some physical system. Okay, so we have the position coordinates, as I said, and the momentum coordinates. And so here's an example. If I write down this Hamiltonian 1/2 q squared plus p squared, that actually, if you want to write down a physical system for which this represents the total energy, you can take a spring, just a spring in the line, and let Q be the position, right? So if I stretch this, so that you think of it as being equilibrium here, but if I stretch it out, then there's potential energy associated to that spring, and that's 1/2 q squared, like, or something like, if the spring constant is chosen correctly, then there's always this potential energy associated to the spring. And then there's the kinetic energy, which is 1/2 p squared, if you assume the mass is 1. Okay, so here's an example of a total energy associated to a physical system. And then Hamilton's equations, or it's like Hamilton's theorem, if you like, says that any trajectory in this system that you assume satisfies the principle of least action, will have to satisfy these differential equations. And so I don't know if I gave the example for the spring. One more. Okay, I don't think I did give an example. But for the spring, for example, if you take dqi dt, so h is 1/2 p squared plus q squared, then, and we just have p and q, then we get the differential equations dq dt equals dh dp, which is p, and dp dt, dp dt is equal to minus q. That defines a vector field in the PQ plane. And it's, I hope dq dt, I think I've got this going in the right direction. So it's a counterclockwise a vector field, and the orbits of this flow are circles tangent to this vector field. The energy is merely the 1/2 the square of the radius of the circle. And since you're moving along a circular orbit, the energy is staying constant. Okay. And so you get this. So this is a general fact that if you write down this vector field associated to the Hamiltonian H, then the flow that it generates is going to have this property that the Hamiltonian itself is a conserved quantity of the flow. And now what Noether's theorem says, or it's not the full weight of Noether's theorem, but part of what it says is that if you have a Hamiltonian flow commuting with another Hamiltonian flow, so imagine the first Hamiltonian flow is this complicated flow that tells you the trajectories of this top, how the top spins. And there's another Hamiltonian flow, which you can even just see in dimension 3, is just the flow that generates a rotation around this axis. And it also does something to momentum. That's also Hamiltonian. And what it says is if one is a symmetry of the other, then the Hamiltonian for the second is also conserved by the first. Right? So if P Hamiltonian and H Hamiltonian, if these two commute, then they actually preserve each other's Hamiltonians as well. They're conserved quantities. So that's the statement. And conversely, if you have a conserved quantity, that actually taking its Hamiltonian will give you a symmetry of the flow. And that's a very useful thing in simplifying differential equations that satisfy that are of a physical nature. You want to solve complicated differential equations, and if you find symmetries in the equations, for example, you can generate symmetries that gives you symmetries of the dynamics, and there's an associated Hamiltonian and so on. So you can reduce dimension of problems by finding symmetries. Maybe physics, intuition in physics tells you symmetries. So anyway, but for me, the moral is that the symmetries of a Hamiltonian flow are very special. They correspond to what we call conservation laws. So you're not just likely to see, at least not Hamiltonian symmetries of a Hamiltonian flow. There's not going to be tons of them out there. They're special. Okay, so now I want to turn to Smail's question. So here's the question that was posed by Smail. So he says, does the typical diffeomorphism F of a closed manifold M have only trivial symmetries, meaning that the symmetry group of F is equal to F, and its iterates? Now, I like this question because it's very general. A has a chance of being true, there's some intuition there. And it's a statement about every diffeomorphism, or typically. There are others. So what is it kind of saying? Well, the typical diffeomorphism should not be symmetric. Okay. Well, if we think of the typical diffeomorphism as just kind of moving points around in some kind of random way, then I guess that makes sense. But there are other things you might ask about typical diffeomorphisms that correspond to points being moved around in a random way that turn out not to be typical. Okay, so this is a meaningful statement that has a chance for holding for, kind of typical diffeomorphisms. Now, what does typical mean? Well, it means large in the universe of dynamics. So if I'm looking at a diffeomorphism, then I want the universe of dynamics it lives in is this group of diffeomorphisms. And this is a topological group. It has the CR topology. So we have a notion of when two diffeomorphisms are close. We just check, make sure all their derivatives are close, and they take points, take a point, goes to two close by points and the derivatives are close and so on. And this is a complete metric space in the CR topology. Let me just emphasize CR topology. And when you say typical, it could mean several things. You could mean dense. So like any diffeomorphism can be approximated by one that has trivial symmetries. That would be what a density means. And generic's even stronger. Generic, a property is generic if it holds on a countable intersection of open and dense subsets. So big in the sense of bare. So here's the definition. A property is generic if I can find a countable intersection of open and dense sets in here so that the property holds on this set. And the bare category theorem tells us that such a set, sometimes called a residual set, is really large. It's dense, but also the intersection of two residual sets is residual. So a property, you could have that a property is dense and the negation of the property is also dense. But you cannot have that a property is generic and its negation is also generic. That doesn't happen. So it's a good, it's a good notion of typical. I guess, are there any questions? Okay. All right, so let's celebrate another woman dynamics, Nancy Capel. So she was most likely asked this question by Steve Smale, who was her advisor back in the 60s. And in her thesis, she answered this question for the circle. So when M is the circle, and for R at least 2. So what her theorem says is, yeah, the CR typical diffeomorphism has only trivial symmetries. So it only commutes with its iterates and nothing else. Okay, so now I didn't say what typical means. So what is typical in this sense? It's something even stronger than generic. So it's open and dense. So not only can I CR approximate any CR diffeomorphism of the circle by something with trivial symmetries, but once I make this approximation, I can't reintroduce symmetry by perturbing it further. So this actually turns out to be false in the C1 topology. It's not open and dense. It's not an open property. So that's just, sorry, that's just the way it is. But anyway, but it holds for any R and even for C infinity. All right, so you could say, what about in higher dimensions? And the answer is there's only partial results known. Unless you work in the C1 topology. And then there's, there's a paper of that I wrote in like 2010 with Bonatti and Crovizier that shows that in the C1 topology, this question has an affirmative answer. So the C1 generic diffeomorphism has only trivial symmetries. Okay. And so just as a side note, because this is kind of interesting, the C1 generic diffeomorphism, therefore, so typical diffeomorphism in the C1 sense, cannot embed in a flow. So I asked this question, I mentioned this earlier, right? If I have an F, remember, if F is the time one map of a flow, then that implies that the symmetry group of F has to contain either, if the flow is not trivial, well, even if it is trivial, it has to either contain the reals or not the complex numbers, the circle. So it has to be big, it has to be uncountable. So a typical diffeomorphism will not have this property. Now, that statement that I just made, that the typical diffeomorphism, C1 generic, does not embed in a flow, was actually proved quite a bit earlier. It's a much simpler statement by Jaco Pallas. So I mentioned this to my Rio-based audience. And what's interesting is that this question is actually, everything's open for CR, where R is 2, say. And it seems to be very difficult. And this question about being embedded in a flow, which is, again, much easier for R equals 1, much easier than the general question, and was proved for R equals 1 ages ago by Pallas, I think is open for R equals 2, as far as I know. That's just a little comment. Okay. Okay, so the last thing I want to say, even just a tiny bit about, I'm sorry, and I actually wanted to mention, because I see Bruno Santiago, he's showing his pretty face. So Bruno and Davio Bata and Martin Legui have some results in various combinations about the centralizer of a typical flow. You would think you can do both questions. You could do flows commuting with it, or you can do diffeomorphisms commuting with it. And you would think that sort of maybe the techniques that Christian and I and Sylvain and I developed would maybe push through not too much difficulty to generic flows. And that is not really the case, but they have some very good special results. Not super special, I should say, but you should look at their work. That's what I want to say. There's some really nice results there, and there's new difficulties that arrive in centralizers of flows. Okay, now, okay, so symmetry rigidity. So this is loosely something that I've been working on recently quite a bit. The idea behind symmetry rigidity is somehow a little bit of extra symmetry should apply, that there's a lot of symmetry in your dynamical system. And I wanted an illustration of this from complex dynamics. And this is not quite what I mean by symmetry rigidity, but it has a similar flavor. So this is an example of a symmetry rigidity type of thing in dynamics. And it's a fairly recent paper of Yusheng Luo, where he proves that if I have a polynomial, or there's more generally for rational maps, but if the Julia set of a polynomial, which is roughly its non-wandering set, has even one symmetry of infinite order. So in other words, if the symmetry group is not finite, then there's only 2 possibilities for the polynomial and for the actual Julia set. And so either the Julia set is a circle, which would happen something like z goes to z to the n as Julia set equal to a circle, or it could be an interval. And here's an example of a degree 2 polynomial that has the interval as its Julia set. And that's so basically the symmetries of Julia sets are always finite. So, and in fact, the symmetry groups in those 2 examples that I gave before are precisely the symmetries I gave you, like the rotation of order 8 and the dihedral group for the snowflake. It really is the snowflake. Okay. Now, in the context of diffeomorphisms, I can just say a few words. This is a joint project with another woman in math, Daniela Damjanovic and Disheng Xu. And just as a sort of a picture of what we're doing. So we look at the space of C infinity diffeomorphisms of M, and we isolate a subset that I would call highly symmetric. So these are systems, maybe they're flows, for example, but even more than just flows, like Anasa flows, like geodesic flows, like flows that come from geometry. So they have like a reasonable amount of symmetry, and we know something about the dynamics. Or affine, things we call affine diffeomorphisms, tend to have extra symmetries, not just they're both kind of rigid in some dynamical kind of abstract sense because they're algebraic, but they also have they have extra symmetry, which we want. Okay, and we assume some chaotic properties for these dynamical systems, namely they are usually partially hyperbolic, which is the kind of dynamics I understand the best. And then we look at a neighborhood. And what does that mean? So we start with these very rigid systems, and then we perturb them a little bit. In the C1 topology is enough, but basically we just take another diffeomorphism that's very close to one of the rigid systems, and either we're basically back in the class of the very rigid system, so we didn't actually perturb it. So this is, you might think of this center line here as representing all the systems. So let me just make a little comment that if I have a diffeomorphism F, and it has some symmetry group S of F, and I have another diffeomorphism, let's say GFG inverse, then its symmetry group is G composed with the symmetry group of F. So that's the symmetry group of this is equal to this. Okay, so that's just an observation. So if I perturb and I'm conjugate, so this is if G is a diffeo. So these highly symmetric systems we should think of as containing the original like affine systems and all of their smooth perturbations, which are in some sense, not smooth perturbations, smooth conjugates. And what we observe in a lot of contexts is a type of symmetry rigidity, which says that if you move away from these highly symmetric systems in here, and you're not conjugate to the original system, you see a precipitous drop in symmetry. And we have some conjectures that make this precise, but this is the kind of theme of the work that we're doing right now, and it's very fun. So that's all I have to say about it. Okay, thank you very much.
Okay, thank you, Amie. Let's thank Amie. So before we open the questions, I would like to announce that we have a draw of a book offered by Applied and Computational Brazilian Mathematical Society, but we are to draw it after the questions. We ask you all to stay, but unfortunately we only can send it by Brazilian address, unfortunately. So if you have a Brazilian address, stay after the Amie's talk, please. Thank you, Amie. Great talk. I loved it. Very, very interesting. And I would like to open to questions or comments. You are welcome.
Hi, Amie.
Hi,
Good night.
Zuzer.
How are you?
I'm good. How are you?
Fine.
Hello,
That
Jose.
my question is, quite innocent in some sense because you just you are changing the name of the centralizers with symmetries. Is
Mhm.
this
Yeah,
the
there's a
main
reason.
Uh-huh.
Yeah, there was a
Yeah.
reason because I wanted to talk about the Julia sets, right? And those are smooth dynamical systems, but they are not invertible. And so there's no sense in saying centralizer,
Okay. Now I
right?
understand.
Do you
Uh-huh.
understand? I mean, I could have looked, it's true, you could look at other smooth dynamical systems that satisfy HF equals, you know, where the other ones are not diffeomorphisms, but that's really has a different flavor. So yeah,
Okay.
because it's not the centralizer unless your map is a diffeomorphism. But indeed, if your map is a diffeomorphism, then the centralizer of F inside the group of diffeomorphism coincides with the symmetry group of F. Yeah.
Yeah, another point is just a comment that this remembers me the work of Elon Lima, that he has the commuting vector fields that after this, I think that Christian made something in this direction related to in some
Commuting
way.
vector fields having a fixed point on the sphere.
Yes.
So Alon, yes, right. So that's actually a nice argument. I think I've made that argument into a homework problem for differential topology class, an extra credit problem. It's a good problem. And then Christian Bonatti proved that if you have two C1 diffeomorphisms of the sphere that are sufficiently C1 close to the identity, then they have a common fixed point. And in fact, that's not true if there's an obstruction if you're not C1 close to the identity.
Yeah.
And there's another.
I think that this is also related with what Bruno made some time ago. No, Bruno?
Yes,
Yes,
Christian
Bruno
also
Davi.
has a paper
More
for
connected, okay,
analytic
that's it.
vector fields in dimension 3 and dimension 4, analytic commuting vector fields in dimension 3 and dimension 4.
Ah, nice.
And when I did my part of my thesis with him, I proposed that he gave me some problem that people in Brazil are not working on, and he said nobody in the world is working on this problem now. So he proposed me to.
Yeah.
Sorry.
Who also works with the centralizers, and then was Paulo Varandas and Wesley Bonomo to have some results about it.
Yeah, so I should mention, yes, those two. Also, Jean-Christophe Yocos and Jaco Pallas.
Yes.
And Todd Fisher, and my former student Lizzie Burslem, and there's others I'm probably forgetting in restricted contexts where you're looking at.
Yes, your context is very broad.
I'm sorry,
all
what?
That is more connected with centralizers. If you change the name by cities, then it is likely to were separated, you know?
Yes.
Well, if you find a paper talking about centralizers of diffeomorphisms, it's a paper about symmetries of diffeomorphisms.
Yes, because the Amie's work is broadest.
Okay, thanks, Amie.
Yeah, thank you for pointing
nice
out
talk.
that. And thank you, Bruno.
Thank you very much. Okay.
Thank you. Any other question, comment? Yes. Okay. If not, let's thank the beautiful talk of Amie again.
Thank you.
Thank you very much, Amie, to accept to talk and celebrate women in mathematics. Again, it's an honor and a great pleasure to have you here. Thank you.
Great.
So if you are in Brazil, we are going to draw the book now. Marisa, Aline, the book name is here. No, I pass to you.
O livro é uma introdução à equivalência de Kolmogorov e Bernoulli, do Gabriel e do Regis. Eu coloquei o nome das pessoas que estão na chamada, que não foram já sorteadas e que estão no Brasil. São 22 pessoas. Número 1. Bruno, você ganhou o livro.
Oh, isso aí é sujeira, cara. Ô, Maria, isso não vale.
Congratulations! Nada,
Não
parabéns!
vale. Olha, Natalina, não, não. Oh, tenha essa tua paciência. Aí não vale.
Tô achando também, viu? Tô achando também.
Aí foi sujeira, foi sujeira. Tá bom.
Ok,
Gente, eu vou
ok,
sair,
gente.
hein?
Obrigada,
Tchau, gente,
Zezé. Obrigada,
obrigada.
gente.
Até
Thank you
mais.
all
E
for
olha,
coming.
Marisa, esse negócio